All right, let's go with it here. So chapter 3, 3.3 particularly, we're going to learn everything there is about division of polynomials. Something you probably have seen in algebra, something called the division algorithm for polynomials. You've raise your hand if you've seen or heard of synthetic division. Synthetic division, going once again. Okay, about half the class. For some reason, that side yes, and this side no. Okay, and then we have something called the remainder theorem, factor theorem. Those two you may have saw as a sort of like definition, but really didn't really work out problems in algebra. So we're really gonna get to the end of how do we divide polynomials. That's sort of like the end of it. So you learned how to factor polynomials and cross off like terms. That was sort of division by factoring. This one's going to be sort of the division algorithm. And what they mean by algorithm is we mean long division. So if you remember long division from a while back in your academic career. All right, real quickly here. So we are going to use the division algorithm to factor eventually here, but we want to get to this whole concept here. If you have a function called f of x, I want to break it up into two functions. A d of x times a q of x. And you have been doing that ever since we've been factoring. Maybe as an example, something like if you had like x squared plus 3x plus 12 or something like that. Let me get this off real quickly here. All right, you have been doing this all along here. So if you have a, let's see, 4x plus 12, something like this, we have broken those down into its factored form. So nothing new here, except what we want to do is we want to go further. We want to go x to the 4th, x to the 5th, x to the 7th, x to the 10th, all those. Okay, so I think we're good to go. Since we're trying to get the two sections today, I'm going to just sort of jump to the practice problems here. So find the quotient and remainder when this happens here. So with factoring, whenever you can factor something, that really means you have a remainder of 0 because you're able to break it down into pieces. There was no remainder. The division algorithm, what it allows for that sort of remainder to be there. All right, and we should think of something called long division. All right, some little shortcuts here to put in place just to make sure we got it. Whenever you write the divisor, this is the number in front, you want to add in all the degrees that you need. So this one has an x squared. It doesn't have an x to the 1. So a lot of times what we do is we put in this little term for x. We can't add anything new to it, so therefore we just put a 0, because 0 times x is still technically 0, but we did put in the placeholder in a sense, what we've done. All right, long division. And the same thing happens for something called the dividend. Dividend is the thing that comes inside here, but of course if you did read 3.3, you know the vocabulary, and if you didn't, then you don't. All right. Putting this in, is the dividend missing any degrees? No. And there's my x to the 2nd, there's my x to the 1, and there's my constant term at the end. And again, this will be review. The next sort of section will be something new here. All right, how do we do this? We look at only the numbers in front or something called the leading term. So x squared is right here. How many times is x squared? Or what do you multiply x squared to give you 3x to the 3rd? We need a 3x, huh? Okay, so we write a 3x, but notice what we do is we write it on top of the column for x to the 1 power. Again, as organized as we possibly can do it. So kind of think of these as columns here. So this is my x cubed column, my x squared column, my x column, my constant column. Okay, 3x now has to multiply all of this right here. So 3x times x squared gives you 3x squared, and it should be that way, right? Because we're trying to cancel off that particular term. It better be that exact same term or else we did something wrong. 3x times 0x really will give you 0x squared. And 3x times 1 will give you a 3x. And so the other part is your polynomial that you're multiplying should end in the same column that you're multiplying with. Okay, and then what always boggled the mind in 4th grade when I learned long division is why in the world do we subtract? But yes, we do subtract. All right, we're getting up to that polynomial but not going over in pre-algebra. In algebra you could go kind of over because you could have negative remainders. Anyways, we learned also that, you know what, if you can do this in your mind, 3x cubed times subtract 3x cubed, 4x squared, subtract a 0x squared, if you can sort of keep all that in your mind of subtracting, sometimes we have negatives here, that's fine. But normally what we do is we change this to addition. And then what we do is we change all the signs inside that other polynomial. Why? Because subtracting is the same thing as adding a negative or adding an opposite. I think it helps because now you can just look down. 3x squared and negative 3x squared, that's gone. Let's see, 4x squared and a 0x squared, that makes a 4x squared. Let's see, a 1x and a negative 3, make a minus 2. All right, bring down the extra little term right here, and the process starts all over again. Have fun. So what multiplies x squared to give you 4x squared? Okay, and then don't forget the signs with it as well. So positive 4, so you're going to put a plus 4. And you guys can finish it off. All yours. Have fun. Cool. All right, I'm going to start as well here. So 4 times x squared gives you 4x squared. 4 times 0x gives you a still 0x. And 4 times 1 is 4. Subtract, or better yet, add the opposite. And let's see, 4x squared goes away. Let's see, there's a negative 2x still there. And 7 and negative 4 make a 3. Okay, for this first problem, again, just getting comfortable with division, what they want you to write is the quotient, so it's just Q usually. That's the stuff that's on top. So 3x plus 4, and then the remainder. Remainder is the stuff that stays at the bottom. And the only other question to ask is, how do you know that you are done dividing?
When we get to the constant term.
Kind of one of two ways. Most of the time is when you get to the constant term. But the first sure way is you look at this x squared and you say, what can I multiply x squared to give you a negative 2x? And notice the degrees are different, right? The degree that you're multiplying with is now lower, or higher than the remaining. So at that point, you know you're done. You can't multiply something if you have a higher degree anymore. Okay, good there. Another practice one here, of course. All right, all yours here from the beginning to end. And give you guys a little bit of time to do this. All right, I'm going to go for it as well here. So first and foremost, hopefully you wrote it out correctly here. So x squared minus x plus 3 is the divisor. It's on the outside. And if you look at the dividend, you notice x cubed is missing. Like, oh, shucks, it's missing. So I got to put a little placeholder in it. X to the 4th plus 0x cubed. There's your 5x squared plus 2x plus 6. And hopefully you are almost done, or at least more than halfway done here. Those of you that are stuck, let's go for it together here. So what do you multiply x squared to give you x to the 4th? X squared gets written on top of the 5x squared then to make that column here. So x squared times x squared, x to the 4th. X squared times a negative makes a negative x cubed, and x squared times a 3 makes a negative 3x squared. Again, subtracting, or even better yet, how about adding its opposite? Let me go back here just for those that are still multiplying through here. So there's my subtraction of it. Alright, so again, changing to addition. So the x to the fourth becomes a negative x to the fourth, the negative x cubed becomes a positive, and positive 3x squared becomes a negative 3x squared. Alright, adding down, x to the fourth are gone. 0 and then 0x cubed and a 1x cubed makes you x cubed. Let's see, if 5 and negative 3 make a positive 2x squared, and bless you. And the next term comes down. And we start the process all over again. Alright, something that multiplies x squared to give you x cubed. So x to the 1 power, it's a positive x to the 1 power, so I have to put a plus x at the end there. And then here we go again. X times x squared is x cubed. X times a negative x makes a negative x squared. X times 3 makes a 3x, and then we subtract. Or add the opposite. Alright, adding the opposite gives you a negative x cubed, a positive x squared, and a negative 3x. Adding down, x cubes cancel. This now gives you a 3x squared. And how about a minus x? And the 6 comes down. And start all over again. Alright, and again, here we go. X squared times what gives you a 3x squared? That would be a plus 3 at the end here. Notice we're at the end. We're at the constant term now. So 3 times x squared is 3x squared. 3 times a negative x gives you a minus 3x. 3 times 3 is 9. And we subtract again. Add the opposite. How about a negative 3x squared, positive 3x, and a minus 9. Adding down, the x squared should cancel, or else we did something wrong. And again, negative x and a 3x make a 2x. 6 and negative 9 make a minus 3. Okay, this time we actually want to write it as a expression. So not just what's the quotient, what's the remainder, but let's see how we can write it as an expression here. So what we do is we write x squared plus x plus 3. Just the quotient as is, and then we're going to add the remainder. Think back all the way to 4th grade. Remember how we added the remainder in as a fraction? It's always what is left over divided by what you were dividing by. So how about a 2x minus 3 on top over your divisor? What you were dividing by itself was x squared minus x plus 3. Cool, there it is. Kind of cool. The division algorithm for polynomials. You could do that all the time. One small problem is that yes, you could divide, but we are more interested in trying to find the zeros. That's the whole quest here. Okay, so we have to learn a few more rules to get us to the zeros of a function. Also notice, whenever this little x to the 4th, x to the 3rd, x to the 2nd, x to the... Aren't these really... The degrees really only just gave us columns, didn't they? If you think about it, all the work that we did were really with the coefficients. Like even going up here, 5x squared minus 3x squared gives you a 2x squared. But really, the x squared gave you the column, but the numbers that we really worked with were just the coefficients. That's kind of... So let's do this here. Let's make this twice as fast. And let's forget about the degrees on the variables. Let's forget about the variables altogether. As long as we have the columns correct, we'll be good. Cool. So this is something called synthetic division. The only thing is, there's one little disclaimer. The only time it could be used is if you are dividing by x minus a. Only if you're dividing by a single factor. So only if you're dividing by a binomial factor with degree 1. So x minus 7 is fine. X minus 3, totally cool. X plus 3 is fine as well, because it's technically just a x minus a negative 3. X minus a half is fine too. X plus 1/4 is fine, but as long as it's a binomial, and as long as it's only degree 1 up here, as long as it's x to the 1 power, subtract a certain constant. Other than that, it works great. All right, quick show of hands here. How many have never heard of synthetic division? Mr. H, I don't know what you're talking about when you say synthetic division. Okay, cool. Got about 3. So let's run through this real quickly here. Let me do it by steps, and then we'll do the problem itself here. So by steps, don't need to write it down. This is just information here. We're going to divide 2x to the 4th minus 3x squared plus 5x minus 63, and we're going to divide it by x plus 3. Notice it is a binomial, and it is degree 1. Okay, so here's what we do. We take this and we actually set it equal to 0. So if you say x plus 3 equals 0, what's the x that makes that 0? Negative 3, of course. This goes its own little box right over here. So you got this little box right here. And you put a negative 3. Then what happens is we keep our columns the same. So x to the 4th column just comes down here, but you don't need the variable. And you don't need the degree here, just the coefficient itself. Hey, we're missing x to the 3rd, is that right? So we're going to put it as 0, just like we did in long division. There's my coefficient for x squared. There's my coefficient for x to the 1, and there's my constant coefficient over here. So all this right here should be up front first, and then we do the problem. How do we do this here? We add down, and we multiply by this number to get to the next column. So literally 2 plus nothing is still 2. Negative 3 times 2 is a negative 6. So we add down and multiply up to the next column. So 0 plus a negative 6, negative 6. Negative 3 times negative 6, there should be an 18 right over here then. Good there? Negative 3 plus 18 is a 15. And we have negative 3 times 15 makes a negative 45. And let me just show you as we go. There's my negative 6. Negative 3 times negative 6 gives you an 18. There's that. So you add down, multiply up. There's my negative 45. Negative 45 plus 5 makes a negative 40. Negative 3 times negative 40 is a 120. And then we get ourselves a 57. Okay, kind of important stuff. This little number all the way at the end, this is your remainder right here. This is 57 would be our remainder. And what we do with these numbers, we put it back into a polynomial. The first term is going to be your constant term, so negative 40. This is your degree 1 coefficient, degree 2 coefficient, and degree 3 coefficient. So we write it back together again. All right, we're good there? With an example here, let's jump to a problem ourselves. Can you divide 2x to the 3rd minus 7x squared plus 5? Divided by x minus 3. All right, those who want to work it out with me here, let's go for it here. So x minus 3, so what is the number that causes x minus 3 to become a 0? This time positive 3, right? Yep. So x minus 3, also if you want to do it like this here, you can say, okay, x minus a is the way the book does it here. It says x minus a is the formula. We have our divisors x minus 3, therefore a is equal to 3. All right, or you can just solve it for 0, whichever way you want to do it. That's kind of the same way. Anyways, a becomes 3, a goes on the outside, What's the coefficients running across? What do you guys say? Two? -7? Cool. Get a 0 there and a 5. Awesome. And some of you guys are done already because it's so easy. Okay, adding down. And what the book does, it puts a little line right here to separate that this guy's going to be the remainder. Some books put a little box right here, whichever order you like. But somehow to separate it so it's not part of that polynomial anymore. Okay, 2 goes down. 2 times 3 is 6. -7 plus 6 is a -1, comes down. 3 times -1 is a -3. 0 and -3 make a -3. And 3 times a -3 is a -9. And we get ourselves a -4. Alright, can you write the quotient that's left and the remainder in one single expression, just like we did on the last practice problem? Alright, so you can do this one of two ways here. If you know you had initially you had x to the 3rd power, you can say, okay, I went down by 1 because I divided by an x to the 1 power. So you know this has to be an x squared to start off with. Okay. You can also count. This is a remainder. This is your constant term. This is your degree 1. So this has to be your degree 2 coefficient. So then we write it as 2x squared minus x minus 3, and then this way you can either put a minus 4 over the remainder, but normally what we want to do is we want to write it like this. So plus, and then you put a -4 on top and an x minus 3 on the bottom. It would be just fine if you just put a minus right here, bless you, and put a 4 over x minus 3. Either or is perfect. Okay, just one more practice problem here before we move on. All yours here. Can you go beginning to end? And tell me if I'm going too fast. I can slow down here, no problem. So from beginning to end, go for it. And then can you write for me that expression with quotient and remainder as one? So first and foremost here, the question is, what is in the world is our a value? So you can either set it up like this, x minus a, and the a value is -3, or you can solve it for 0. Subtract 3 from both sides gets you -3, but in all cases here, -3 goes in the corner. Bless you. And let's see what we put down here. We got a 2, a 1, -18, and -7. We good? That down, move across here, put a little border line for our remainder here. Cool, and then let's go for it here. So adding down 2 times -3 is a -6, -6 plus 1 is a -5, -5 times -3 is 15, -18 plus 15 is a -3, and -3 times -3 is a +9, and then adding down gets you a 2. So quick show of hands, how many at least got the numbers correct completely as our sweet. Okay, and then the quotient is going to be a 2x squared minus 5x minus 3 plus a remainder of 2 over x plus 3. Cool. Not bad. Math is easy for the most part. If you read ahead. If you try the homework. Okay, so again, the whole concept we're trying to get to is trying to get to the zeros here. still another step to get to the zeros here. Here's what I want to do. I want to be able to, instead of doing long division, instead of doing synthetic division, what I'm really concerned about is this little remainder right here. So now the next question is, how do I get through all this stuff? How can I get to the remainder even faster? Is there a way to get to this remainder even faster? That's the question. How can I get a 2 out of all this? And the funny thing is if you were to plug in a -3, and you guys do it, go for it, go for it. Plug in a -3 into this x value right here, and right here, and just see what you guys come up with. I'll do it as well. So 2 times -3 cubed plus -3 squared minus 8 times -3, sorry. See what we got here. Let's see. That's -27, -54. You guys watch me, make sure I do it correctly here. 9. Is that positive 54 then? How interesting. Those two cancel, is that right? Positive 2? That's so cool. So plugging in the value itself will actually give us the remainder right away. That's awesome. So that's what this says right here. It's called the remainder theorem. Remainder theorem says if you're dividing by x minus a, all you really got to do, if you're just trying to find out your remainder, you just plug in the a into the f function and you get that part called the remainder. Again, as long as you're dividing by a binomial of degree 1. So whenever you can do synthetic division, if you're just interested in remainder. Okay, an example, and then we'll jump to our practice problem here first. An example problem from the textbook here. So we are trying to find the remainder of a polynomial, this guy here, blah, 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 blah. And we're going to divide it by x minus 1. So kind of careful. We could use synthetic division if we really wanted to. But a little bit even easier, just plug in a positive 1 into a function itself. And we get ourselves a -2. And so that would be the remainder if we were to do long division or if we were to do synthetic division. We would still get a remainder of -2. Okay. So then now the question is, Mr. H, why, I could just do synthetic division right away as well, and I could do long division. Remember how we have to fill in those zeros all the time, right? Because if you're missing degrees. So now the question is, you guys want to fill in the zeros here?
Yeah.
Okay, you three go for it. And the rest of the class is going to do this here. Can you find the remainder if x to the 110th power minus 2x to the 57th power plus 5 is divided by x minus 1? Alright, hopefully you guys finished it off here, but I have a 1 that I'm going to plug in. We're good there, because x minus 1 is the one that gives me the 0. And as I plug in 1 into the function itself, I get myself a 1 minus 2 plus 5, or how about just 4? Cool. Alright, so that was the remainder theorem. This means that I can plug in the number itself, get the remainder. Let's go backwards. So we know we can use synthetic division, we know we can use let's go backwards. So how about this? Let's use synthetic division to find the remainder. Cool. So the way it's worded is like this. Is can you find f of negative 2? But can you do that using synthetic division? Why do we do it sometimes? Because sometimes the numbers might become humongous. Like how about plugging in, instead of a negative 2, what happens if you're plugging in negative 25? I'm not sure if we want to do a negative 25, plugging in, try to get that by hand. But synthetic division sometimes gets you a little faster. So all yours. I think you guys know how to do the synthetic division. Got only issue is what are you going to use as this corner number right here? Just negative 2, right? That's the number that you are plugging in. All right, give you guys a little time. Try it yourself. Go for it. Let's look at this together here. So the 1 comes down for x to the 4th, or degree 4. We are missing degree 3, so that has to add in a 0. That's the other mistake I've seen students make. Then the 2 comes down, degree 2. The coefficient for that is 10. So how about a 2 and a negative 20 at the end here? Again, that little bar line, separate the remainder. And the stuff is easy here. 1 goes down, negative 2 times 1 is negative 2. Negative 2 times negative 2 is a 4. 14 comes down. Now we got ourselves a negative 28. Plus 2 gets you a negative 26. And the numbers are getting bigger and bigger here. Multiply by negative 2, how about a 52? And adding with the negative 20 gets you a 32 at the end. And again, all we were interested in is just the remainder, right? We're not interested in the quotient. So find for me f of negative 2. We say, okay, that's easy. F of negative 2 is 32. There it is. Okay, finally we get to what we want to get to here, something called the zeros. We're finally able to get to the zeros, putting a few things together, and one more theorem that we have to put together. Something called the factor theorem. Bless you. Factor theorem. Of course, as you're paying attention to the book, we're on page 330 in the textbook. Factor theorem just says this. If you have a remainder of 0, that means if you plug in f of a is equal to 0, that means x minus a is actually a factor of f of x. Interesting. Quick example. Let's do this here. The easy one here. How about 7x plus 12? If I were to plug in a 4 into this, negative 4 maybe. Not a 0. Bless you. Alright, what do you guys say with this one? Minus 28 plus 12 makes 0. Alright, in that case, that means this can be written as x, actually technically it's subtracting a negative 4, right? Which really is just x plus 4. And then we know from factoring, we know this has to be an x plus 3. So notice because the remainder theorem worked, gave us a remainder of 0, I can write that in a more factored form. Okay, we're good there? Again, putting pieces together here. Let's walk through this one here. As we do, I think we'll be good. So let's see, can we solve this equation? 3x cubed minus x squared plus 20x minus 12 equals 0. Given that we already know that negative 2 is a solution. Now Now, since we know that -2 is already a solution, we already know the remainder is going to be 0, right? But we're not interested in the remainder. We're interested in what is left over. So we can either do long division, or in this case, you think we can do synthetic division or no? Yeah, if you say one of the solutions is -2, aren't you saying x equals -2? Right, it's a polynomial, so that's cool. Let's go for it then. Let's put this -2 in our little box. And let's go with, let's see, quotients would be 3, or coefficients would be 3, -1, -20, and -12. Cool. And we assume we should get a remainder. Actually, we know we should get a remainder of 0. We assume the remainder is going to be 0. If we get something other than 0, we did something wrong. Alright, hopefully you guys are staying ahead of me here. I'm going to try to catch up though. So 3 goes down, 3 times the -2 is -6. -6 and 1 make -7, and then times by -2 makes a 14. Add with the -20, how about a -6 this time? Hey, perfect. -2 times -6 is a 12, and I get my remainder of 0. Okay, what am I interested in this time? Not the remainder. I'm interested in this part right here that's left over. So if I know that -2 is a solution, don't I know that x plus 2 is a factor? Now, what is my remaining polynomial that's left? 3x squared minus 7x minus 6. Perfect. Okay, now, once we got it down to x squared, can we do a little bit of factoring to finish it off? Yep, this is the fun part of factoring, isn't it? Where you have to guess and check here. Only way I get a 3x squared is a 3x times x. Now I need multiples of -6 in here, so the outside inside terms give me a -7. I'll let you guys try that yourself. Good, I heard -3 and 2, and I heard 6 and 1, so one of them's right. Alright, I'm going to go with a +2 and a -3 in there. As 3 times a -3 makes a -9. 2 times 1 is a 2, so -9 subtract 2 makes a -7. Alright, if that's the case, tell me if you guys agree here. That means if you scoot the 2 over, divide by 3, you get a -2/3. If you add the 3, you get an answer of 3. Okay, so solve this equation. If you understand that one of the solutions is -2, that means all the solutions would be -2, that's already given, and -3 halves, I'm sorry, -2/3, sorry, and a 3. Good, there's my 3 answers of that if I know one of them already. This is so cool. We have solved a generic x cubed equation, which we have not been able to do in algebra. Because we were only stuck with, let's see, we were only stuck with x squared, right? And then there's 2 forms that we learned for x cubed. The sum of 2 cubes and the difference of 2 cubes, right? Those are the only 2 that we were able to solve. So now we've solved a generic cubic equation. That's awesome. Okay. If you can't factor, if you were not able to factor 3x squared minus 7x plus minus 6 equals 0, what should have you done? Quadratic formula. That's the only thing that's left. Once you get down to x squared, you got a whole bunch of good tools. Factoring if it's easy, if not, you just move on to quadratic formula. Okay, so let me do this here. I think we have enough time to see if we have enough time to put this together. Oh yeah. So let me do the word problem here. I love word problems. Sometimes we don't get to it. I know you hate word problems. That's why I love them. So we got a petroleum consumption C in something called quads. Interesting. And those are not for wheeled vehicles that you ride on. in the United States. So petroleum consumption in the U.S. from 1993 to 2011 can be modeled by this equation right here. T is equal to 0. It represents 1993. And again, the model indicates that if you plug in a 4 into here, you're going to get 6.8 billion. So now we want to do this. We want to find another model between 1997 and 2011, where the model estimates consumption of 6.8 billion barrels. Again, this is the example problem. Haven't even got to the practice problem. This is for us to, don't write, just kind of think with me here. Okay, so C4 is equal to 6.8 billion, is that right? That's the remainder. There's a little tricky part to this here. So, if that's the case, are we really saying that if you plug in a 4, you get 6.8? And so let's see if this makes sense here. It says if t is equal to 4, we plug this in. This is the tricky part right here. C of 4 is equal to 6.8, therefore C of t is equal to t minus 4. There's my quotient, and a 6.8 being my remainder. Got some interesting concepts here. If you subtract 6.8 from this right here, wouldn't you get a 0? Is that right? Wouldn't you get actually a 0? Because t of 4 would give you 6.8, but if you subtract 6.8, that means you get a 0. That means you got yourself a factor of t minus 4. And here's your remaining quotient. Kind of fun stuff there. So here's what we're going to do. If we're going to start off at 2007 being the 0 for us, the relationship is that f of t is equal to the original formula subtract 6.8. If that's the case, we make ourselves a little formula. We just take the function itself, subtract 6.8. And we have ourselves a model using the same model, but just updated 4 years later now. All right, so then let's see if this makes sense here. Finding another year between 1997 and 2011 where the crude oil petroleum was 6.8 barrels requires us to find another 0 somewhere between 4 and 18. So now the question is, we got to find ourselves a 0 somewhere between t is equal to 4 and t is equal to 18. How do we do that? Very carefully. Factoring or quadratic formula. Kind of gonna go with quadratic formula. Is that okay? I've never learned how to factor decimals before. Okay, so using the quadratic formula, we find blah, 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 as we work, we find that a year t equals 17. Now t negative 11, that's not going to work, right? Can't have negative time. But at t is equal 17, that actually gives us our 0 that we want. Okay, if that's the case, let's see if this makes sense here. So then, because t needs to be between 1997 minus 1994, so between 4 and 18. This model really just says that 2010 the crude oil consumption was 6.8 billion barrels. We good? Let's try our problem, see if this makes sense here. Let's go for it here. I think as you start writing it down, it might make a little bit more sense and a little slower. So the value c of x, here's our formula. As you guys are doing that, let me draw a little something here. In order to get a polynomial, at least a rough sketch of a polynomial, what we really are trying to do is we're just trying to find another point, because as long as we have 2 points or 3 points, now we know where we can actually make the sketch of the polynomial, because that's what we're trying to do. So let's go for it here. Let me do it this way here. So f of x, original function, and I'm going to write it down underneath. It should be horizontal across here. So see if this makes sense. F of c minus 10. So f of x equals c of x minus 10. Okay, so what we're going to do is we're going to write this function again. And all we're going to have to do is just subtract 10 all the way at our constant term right over here. So instead of 41.05, it's going to be a 31.05. So we just subtracted 10 right here. And we've updated our function in terms of years. By 3 years, basically. X equals 3. All right, what we want to do now is we want to get this little something called q of x. It's this polynomial here. Let me go back real quick just so we see it. So this right here was our 10. We know it's going to be t minus 3 for us because of the 3 here. We need to figure out what in the world is q of t. That's our function. What's this function right here? That's the leftover. What's the quotient that's left over? And so what we do, we plug in, because we know the 3 is the one that gives us the 0. We plug in this function to figure out this little remainder that's left over. Remainder should be 0, and we should wind up with a polynomial that's left over. Alright, writing it down, let's see, 0.23 multiplied by 3, and lots of good decimal work here. I'm going to let you guys finish it up.
Let's examine one of the more problems.
Finish off this, because this is going to give us our quotient right here. So as I add down, gives me a negative 3.565, multiplied by 3 gives me a negative 10.695, adding down, and multiplying to the next column, and get yourself the 0. Alright, why was that important? Because I needed this polynomial right here. So this is x cubed. Now I know I'm in x squared. So 0.23 x squared, negative 3.565, x minus 10.35 is my leftover polynomial. Okay, and all I want to do with this polynomial is figure out where does it hit another 0. And once I know that, I have 2 points. Of my polynomial, and then I can pretty much graph it because I know all the zeros between them. Okay, setting this guy equal to 0. And again, factoring, I don't think so. Quadratic formula, yes, I think so. Okay, not going to bore you with the math here. It's going to be all over all that right there. And you probably just want to punch it into a calculator. And again, if you want to, that's fine. we're kind of a little bit stressed on time here. I just want to at least give you the numbers here. And if you do that on a calculator here, you eventually wind up with a term that has something like this in it, and eventually you get yourself 18 or a negative 2.5. Not bad. Okay, we reject the negative 2.5. And let's see, original function is 1993, 18 years after 1993. $2011.
Well, I was just adding that year.
Say again?
I was just adding that year, that's why I
Okay, got it. Anyways, just an example there to sort of see where this stuff is sort of used at, and a little trick there of how you can scoot a polynomial and get the remaining quotient.